to make a gridding. So maybe I finally figured out how to do that, but maybe if somebody else tried to do this, they don't need to go to Google and find how to do it.
Okay.
Because I think in may use the grid file was done.
Right. That was done, and actually the way that they construct a grid file in the online text seems to be quite convoluted. So you found a solution.
I think so.
Okay. Well, why don't you email me the script and the link, and I'll post it to the guest page.
What library do you use?
Not sure which one of these, but I think it's SP or GStat.
Yeah, as I recall, the tricky thing is setting the right bounding box. Figuring out how to set the right bounding box that lines up appropriately with the data. Okay, so today we're going to talk about time series analysis, and there's three. Well, there are many topics in time series analysis. There's three that we're going to talk about. The first is ARIMA modeling, which is kind of a classic approach to time series analysis. It's used a lot for financial forecasting. That's really one of the biggest areas it's used in. Spectral models, which focus on detecting and quantifying periodic components in a time series, and then coming back again to how to do regression when you're working with temporal data where the errors themselves may be temporally autocorrelated. And in fact, the solution is very similar to the solution you're doing spatial regression. It's just a different kind of correlation structure. So today we're going to focus on ARIMA models. Has any of you studied ARIMA models? Okay. There's a very nice textbook that's available online through the library. It's new. I think it's sort of 2011 or 2010, 2011. That is short, pretty easy to read, has lots of examples. It was actually quite refreshing, because back when I first learned this stuff, all the textbooks I found were quite opaque. And this is really nice, clear, and not not long and neither long nor dense. It just sort of hits just the right things.
Does it have like software examples, or is it just?
It doesn't. It doesn't have software examples. It's conceptual. But I mean, there are other online resources that say how to do time series analysis in R. In addition to time series analysis per se, it has a nice chapter on visualizing data and some of the issues about how to scale graphs and how to set aspect ratios to actually demonstrate the features that you want to see, or even to be able to see the features that you want to see. I think that's chapter 2. So I've put it so you can find this if you go to the library website and search for time series analysis. This will be like the 4th thing on the list. I've also bundled up PDFs of the 5 sort of core chapters and put them on the GaptoSpace website. Okay, so we're talking about analyzing time series, and all of the analyses of time series assume something called stationarity, right? Which simply means that there aren't, that sort of the averages expected value. I mean, conditional. There's always a conditionality on recent past, but apart from that conditionality, the expected value of the observation is and the variance around those expected value is constant. So this is an interesting example. Is this time series stationary? Okay, so I mean, you know, if you look at over the long time period, it's kind of, it seems, you know, the averages are here around the center of the picture. And, you know, if we were looking at long time differences, right, if we continue this out for many hours, years, time, and minutes, then I think we probably could treat it as stationary. But if we're actually interested in what's going on from minute to minute, then, you know, it's clearly not stationary. There's, you know, very long runs of heading in one, trending in one direction and trending in another. So the whole notion of what counts as stationary is, to a large degree, scale dependent in terms of both the length of the time series and the intervals between observations that you care about. I mean, it could well be that this is just a badly oversampled time series, right? And then if we sampled it once an hour, we could treat it as a stationary time series. But in that case, we'd only have 4 data points. So in this case, we assume, you know, presumably there's interest in understanding what's going on in this minute-to-minute variation. Here's a couple more examples. So here's this time series. Is not as smooth as the previous one, but we still see kind of some kind of trend that looks like that. And that's when we start looking at autocorrelation functions, that's going to show up as artifacts that make it difficult, basically make it impossible to apply the ARIMA models. And here's a third example of non-stationarity. We have, you know, a clear trend. We have an increasing variance through time, and we have very regular seasonal cycles. This is not the CO2 record. This is airline passenger data, but the CO2 record, no, that's too unlike that. And the interesting thing here to note as well is that the trend is probably not linear. So we'll have to deal with that as well. So for now, we'll come back to how you how we deal with non-stationarity. But let's start by assuming that we have a stationary time series. And so there are two components of ARIMA models, the autoregressive part and the moving average part. So I will try to follow the notation that's from this textbook. And so typically we'll use ZT or WT to represent the time series. And I think that, although it doesn't explicitly say it here, Z can be sort of any time series data. W is assumed to be a stationary time series. And then if we're looking, say, at ZT, then we'll call, if we subtract from it the mean of the time series, that will be called ZT with the tilde. Okay. And differently from most texts that I've worked with. The noise term, the sort of the random shock that occurs every time, is given by AT. So the basic model, suppose we have a process in which the current value from the time series has some correlation with the previous value. Okay, there's a causal relationship between the previous time value and the current time value. Right, and one example that, in the field that I work in, if we're talking about, say, a population model, right, where NFT plus 1 is births minus deaths rates times NFT plus some noise, right? Here is sort of the built-in correlation, structural correlation, causal correlation between the number of individuals at one time period and the number of individuals at the next time period. Okay, so the basic model here for a would be that there we go. That ZT, I'm going to write this, ZT tilde equals phi times ZT minus 1 tilde plus AT. Okay, so what this is saying, right, we're using the tildes. So what this really says is that the deviation from the mean, which is, so this says ZT minus mu equals phi times ZT minus 1 minus mu plus A. So it says that the deviation from the mean is correlated with previous deviation from the mean with correlation coefficient phi. So often, it's the reason we think what the mean is just because it's easier to do the equations here. So it's
And we're done.
Okay, and so this is called an AR1 process. So AR for autoregressive, 1 for having a single a single component here. So in general, an ARP model says that ZT tilde equals V1 times ZT minus 1 tilde plus V2 times VT minus 2 tilde all the way out to P terms. Plus P error, the red chalk. Okay. And this can be, I mean, in terms of what this actually represents, this could be, I mean, there could be sort of direct causal links to the distant past. There could this structure, this statistical structure, can also represent the lagged effects of other variables that are interacting with the variable that you're measuring. Okay, so commonly, for example, in a population model, if it's instead of a single species population model, there's an interaction between a predator and a prey, and all you have is observations of the prey. You can often reconstruct the dynamics using an AR2 model, where that second lag, is representing the hidden effects of the predator dynamics, which are themselves affected by the prey dynamics. um, So, one thing to think about here is, so I didn't say if there's any constraints on what these fees could be. So if fee is less than 1, then, aside from the random term, this year's deviation from the mean is going to be smaller than last year's deviation. Last time's deviation from the mean. So you're going to tend to get observations coming back towards the mean, okay, which is what we want if for the process to be stationary. And in fact, you can, there's a formula that says, if phi is less than 1, then you can write down, well, you can show that the mean of the process is mu, and you can write down the variance of the process as a function of the variance of the A's and the strength of the correlation. If the correlation is 1, then really all you're doing, basically you're saying that the current value is the previous value plus a random shock. Okay, so that actually gives you a random walk. And a random walk, the variance of a random walk goes to infinity as time goes to infinity. And if phi is larger than 1, the process actually diverges even faster. Okay, so for stationarity, which is to say a constant mean and a constant variance, requires phi less than 1. Okay, and then in the more general case, you can write down if there's a characteristic polynomial that you can write down, and the roots of that polynomial have to be within the unit circle. So it uses they'll be complex, and all of them have to have, in the complex plane, they have to have magnitude less than 1. Okay, so not all autoregressive processes are stationary. That's an important thing to know. So here's an example. So what does an AR2 process look like? This is real data that turns out to have an AR2 structure. And in this case, you can see that nearby observations seem to be correlated. And there's actually kind of a almost regular cycle of period, 10 hours or so. And certain kinds of AR2 models will give you that pattern. So how do we analyze a time series like this? What we want to look at is what is the empirical correlation. So if we look at a plot of temperature versus lag 1 temperature, so that's temperature 1 time period before, we see quite a strong correlation. If we look at the second lag, there's a much weaker correlation. As we get out to the third and fourth lags, there's not a whole lot of correlation at all. Okay, and so we can summarize that with this autocorrelation plot. Right, so this says the height of these bars are the correlation coefficients, and these are just the empirical correlations between ZT and ZT minus 1, between ZT and ZT minus 2, between ZT and ZT minus 3, and so forth. And so what we see is a strong correlation at lag 1, much weaker correlation at lag 2, and not much correlation to speak of at higher level. Okay, so getting used to, so this kind of plot is sort of fundamental in this kind of time series analysis. So getting used to looking at these plots and understanding what they mean, right? This 0.65 or this 0.7 refers to the strong correlation between temperature at time t and temperature at time t minus 1. And the thing to notice here is this kind of exponential decay of the correlation as you go to longer time frames. This dashed line represents an approximate 95% significance test for the correlations being different from 0. Really what we see is just one significant correlation.
What is this in Boeing?
Well, generally, yeah, let's see. So, really this whole band should get wider as you go out, because as you go to longer lags, you have fewer pairs with which to calculate the correlation. Different software is different about what it does. R just sort of picks an average value and plots it straight across. Whatever software they were using to make this plot calculates, I guess, a different value for lag 1 than everything else.
Just wanted to real.
Yeah, it's
So it should, I mean.
it's an approximate level. I wouldn't make a big deal about whether this was just below or just above the threshold, but it's just sort of right on the margin of not being significant at the 0.05 level. Some software, including R, will also plot a autocorrelation at lag 0. And what's the value of that? What's the autocorrelation at lag 0? Going to be
1?
1. Yes, the correlation of ZT with itself, right? So when you look at this in R, there'll be another spike that goes up to 1. So I told you that this comes from an AR2 process, and yet this second lag doesn't look very meaningful. But this correlation is, you could think of it as the sort of as the total correlation, or the unconditional correlation between temperature and the second lag of temperature. But if you think of the autoregressive model as being like a multiple regression, the coefficients of that autoregressive equation are going to be the partial the partial coefficients, right? So we actually need to be able to estimate the correlation between lag 2 and lag 2 after taking into account the strength of the correlation at lag 1. Okay, so because even if there is only Suppose we have an AR1 process, so that here's our model. This is truth, right? Well, and suppose this is really what's going on. Well, what's ZT minus 1? ZT minus 1 is B times ZT minus 2 plus AT minus 1. So if we substitute this into here, we get ZT equals B times correlation between ZT and ZT minus 2 is just going to be V squared. Okay? So even though there's no actual direct link between these two variables, the sort of compounding of the autocorrelation results in an empirical observation of that correlation. So what we need is to basically have a way of saying, well, is there any correlation after we take into account that first order correlation? And so this is directly analogous to a multiple regression problem. And so in time series analysis, this is done through something called the partial autocorrelation function. And so we see the same estimate of correlation at lag 1, but now we see a negative estimate at lag 2. Right. And so this is, and then see that it very abruptly goes to 0 thereafter. And so an auto regressive process tends to have an autocorrelation function that dies down kind of exponentially to the axis. It may do it through sort of in a kind of cyclic way, and it often dies down less quickly than this. And then it has a partial autocorrelation function that goes to 0 very abruptly after a certain number of lags. And so the indicator then, if you're trying to ask, well, what should I use for P, right? How many lags should I include? It's the number of significant lags in the partial autocorrelation function. So this is a process with a positive correlation at lag 1 and a negative correlation at lag 2. And that combination of positive at lag 1 and negative at lag 2 is what tends to give these kind of cyclic, almost periodic dynamics. So how do we estimate this? Basically, it's you write down, once you specify the model with a certain number of lags. I mean, it's basically a regression equation at that point. So it's in fact, I think for a simple AR model, it can be solved with regression. Okay, so the second part of the ARIMA model is the moving average. Okay, and moving average. So before the autoregressive part was some sort of there's a link between ZT and ZT minus 1. Okay, it could be a direct causal link. It could be through the operation of an unobserved variable that is itself autocorrelated. The moving average component says that what we see today is simply a weighted average. Doesn't depend on the past value of Z. It depends on the past values of the shocks of the noise terms. So let's take a look at that. there's some driver, or some series of random shocks that drives the system. And the output variable that we care about is a weighted average of sort of the recent random shocks. Okay, and you might think about, well, suppose you're looking at rainfall, or sorry, if you're looking at stream flow, and the random shocks are rainfall events, right? You care not just about rainfall in the current period, but rainfall in the previous period is going to have an influence as well. Less of an influence, but it will have an influence. And so more generally, an MAQ model just says that ZT is AT plus theta 1 times AT minus 1 all the way out to theta q times AT minus.
Plus or minus?
Sorry, minus.
Minus.
It's a arbitrary convention that I hold. It's hard to remember. And in fact, it's so arbitrary that the help file in R for the ARIMA model says that it reports the moving average coefficient with the opposite sign of some other software.
Oh.
And again, you typically expect, you know, that these thetas are going to be less than 1, right? If they're, you know, you expect the past to have less weight than the present. So here's an example of a time series that has an MA1 structure. And it's stationary, it has mean 0. What this actually is some stream flow data, annual stream flow data that I've done that wasn't stationary, that I did some manipulation to make it stationary. Okay, and you know, it's time series, it jumps up and down. It seems like there's some regularity to it. If we look at the autocorrelation function, we see, so this now is this is an analysis I ran in R. So here's the lag 0 autocorrelation. There's a lag 1 negative autocorrelation, and then basically goes straight to 0, right? And in contrast, the partial autocorrelation function has a much more gradual decay towards 0. Yeah.
Why you could use the autocorrelation if you actually are going to need the partial autocorrelation to decide which lags? Or
So if you're in the autoregressive model, you're right, it's the partial autocorrelation function that tells you something about which lags are meaningful. And in fact, this gives you a pretty good first approximation to what those partial correlation the fees should be. But now we're looking at a different process, a moving average process that the model doesn't explicitly include a correlation between ZT and ZT minus 1. There, you know, one emerges, right? But this autocorrelation is not in that model, right? There's no fees in that moving average model.
AT has some property? Like the noise model has property?
Sorry, say that again?
The AT, the noise model has some property?
Oh, so the noise, sorry, the noise has mean zero. It's typically assumed to be IID, independent and identically distributed, and for sort of the standard fitting routines, it's assumed to be normally distributed. I mean, it's using a normal likelihood model to estimate the parameters. And you can, once you fit the model, you can test that. You can look for are the residuals from the fitted model normally distributed? Is there a temporal correlation in residuals? The variances seem to be constant with time and so forth. So this pattern of, it's time series, this branch of time series analysis has a bit of, it all seems a little bit mystical because it was developed very empirically, and so the pattern that emerges from these two kinds of models. So an autoregressive process gives a gradually decaying autocorrelation function and an abruptly decaying partial autocorrelation function. A moving average process, it turns out, gives you exactly the opposite, right? So this is the autocorrelation function, not of the ATs, but of the ZTs. Okay, so we have an abrupt decay of the ACF and a gradual decay of the PACF, which is an indication of a moving average model, and the fact that there's only one significant lag in the ACF is the indicator that there's simply one term in the moving average model. Okay, so this suggests that this is an MA1 process. So, here's sort of the summary. So here's the models, the AR model, and we typically, or conventionally, we use P to represent the number of autoregressive terms. The ACF has an exponential, kind of damped exponential pattern or damped sine wave pattern that tails off gradually. The PACF cuts off quite abruptly after P lags. Okay, and if you construct an AR model and simulate it, this is the pattern. This is exactly the pattern you see. The example I showed you is actual data, so it's a little bit messier. The MA process, here's the equation. Now it's the ACF, the autocorrelation function, that cuts off abruptly after Q lags, and the partial autocorrelation function decays slowly. Okay, so this is, so if you see one of either this pattern or this pattern, you can tell you, well, it's an AR process or it's an MA process, autoregressive or moving average. And then you pick, you use this to say, well, how many lags do I use? And then ask the computer to fit it for you. Or how many lags do I need to use for the MA model? In many cases, you can imagine processes that involve both autoregressive and moving average components. So here's the model, here's the autoregressive part, here's the moving average part, and then in that case, you find that neither the ACF nor the PACF has an abrupt cutoff. And so choosing the P and Q, it becomes a bit more challenging.
What happens if we choose the wrong P or Q, or more P than than we is exactly needed?
So if you choose too many lags, then the higher order lags will probably be estimated close to zero. It's just like including in a regression model, including variables that aren't actually informative.
So it's not like they are going to affect the prediction. It's just you are.
Well, they are going. I mean, they will affect. They'll affect the uncertainty in the predictions, right? Because there's the other parameters will have larger standard errors because you've got these extra parameters in there. So typically the goal is to try and find, a model that seems about right. Once you start having mixtures of autoregressive and moving average terms, it's not always obvious exactly what the right solution is, because you can get patterns, models that fit almost equally well that have, say, a P of 2 and a Q of 1, or maybe a P of 1 and a Q of 3 or something like that. So there's different combinations of P's and Q's that are not exactly the same process, but are similar enough that over a finite time series, they seem to fit somewhat similar. Okay, and so most, you can, right, sort of imagine all combinations of P's and Q's that are plausible, fit all those models and compare them using something like AIC. And what you'll often find is that there's 2 or 3 models that aren't that different in AIC. And so then the distinction, how to distinguish among them, well, you rely on what you know about the actual physical process that you're modeling to see whether it makes more sense to think of it as being a serial dependence of the variable on itself versus a dependence on some window of these input shocks. But you also look at which one gives the least autocorrelation in the residuals, right? Is sort of which model seems to subtract the structure out of the residuals most more effectively, as opposed to, and that may be a more important indicator than which one has a slightly lower sum of squared errors. So just to go through some examples to see kind of canonically what these look like. So these now are actual simulations. So here's an AR1 model. So P and Q, and we'll come back to D, but all of these have a D of 0. So here's an AR1 model with a positive coefficient. Here's what the time series looks like. Here's the quite slowly decaying autocorrelation function and abruptly decaying PACF with just one lag. An AR2 model, which is similar to the first one we looked at. Again, ACF decays slowly, and here we have two significant correlations with PACF. And this is with both, and this is a case where both are positive. Here's one like the one we started out looking at where the second lag is negative, and so it's a stronger pattern than the first one we looked at. So we actually see this kind of decayed cycle going on, which represents basically, this represents the cycle is strong enough that at lag 1, 2, 3, 4, 5, 6, this is basically a period 6 cycle, and so these peaks are on average 6 time units apart. And again, the PACF just suddenly stops pretty suddenly after two lags. In this case, it's interesting. The second lag is actually in this plot, although the actual coefficients, second one is small. So here are some moving average processes. This is similar to the one we just looked at. It's a moving average with just the first term, and we see one spike in the ACF, a decaying pattern in the PACF. Here is two terms in the moving average function, and this is somewhat less clear, but we see that kind of the ACF seems to drop off after lag 2, and the PACF, it's not clear what's going on. It might be a little bit of a cyclic pattern. And then here's what happens when we have a strong autocorrelation, autoregression coefficient, and a moving average component. What we end up with is that something that over the time period that we're looking at doesn't even look that stationary. And this is, you know, for a process that seems to wander around a bit like that. This is the kind of pattern we often see in the ACF. And then the you know, here it sort of oscillates back with a period, back and forth with a period too, but it is still sort of gradually decaying. So typically in this situation, what would you say? You'd say that the autocorrelation is giving you, autoregressive process is giving you this pattern, the moving average process is giving you this pattern. You sort of, and then you basically start off by saying, well, let's try one lag at each, and seeing, you know, and then look at the residuals and see if there's any additional structure that needs to be dealt with. Okay, so diagnosing non-stationarity. You know, you can sort of gaze at it the way we've been doing, but if you can actually, you know, non-stationarity of this kind, where there just seems to be drift that moves the system around, shows up as these lots and lots and lots of large correlations at long lags in the autocorrelation function. You can also look at it by looking at a variogram, which is directly analogous to the spatial variogram, but now we're looking at distance in this axis is distance in time rather than distance in space. So this is you know, the variance at lag 1, the variance, basically the squared difference between zt and zt minus 1, dt and zt minus 2, and so forth. So this is the original time series. When we do the variogram of that, we see that, you know, the farther we go out, the greater the variance gets. There's no sort of plateau. With a stationary process, you expect that eventually the variance is going to asymptote to the stationary variance of the process. So these are two examples of time series that do have reasonable stationarity. Okay, so again, we're looking for, on the time scale that we're interested in, we're looking for conversions to some kind of what a geostatistician would call a SIL. So how do you, if you have a non-stationary time series, and then also if we had a periodic time series, then what we'd see is a really strong pattern where the ACF is really periodic, and that periodicity dabs down very, very slowly. Or, you know, in the case of a seasonal cycle where there really is a period of 12 months, it may never damp down, right? There may, every 12 months there'll be a peak in the ACF that's well above the significant threshold. So what are the solutions? The standard solution is differencing. Okay, so you take, instead of analyzing ZT, you analyze the difference between ZT and ZT minus 1. So we create a new variable, which is the changes in Z. And that is a single difference often will get you what you need, right? So if you have a linear trend in the mean, right, a single difference will turn that into a stationary time series with a constant mean, right? Where the constant mean, the mean of the new series is the average rate of increase in the original series, or the average absolute increase in the original series. If you have a series like this, first differencing also typically gets you what you need. Okay, and so this variogram is the variogram of the first difference of that time series. Sometimes that's not enough, right? If you have a quadratic trend in your data, then after you difference it, the difference time series will have a linear trend. And so then you need to difference it again. And so that's why they sort of difference it again to see if that got any better. It really is pretty much the same in terms of its stationarity.
So that second difference is the difference of the difference.
Right. Right. So let's see, where's the notation? So you can write the standard notation is that the difference operator is denoted by an upside down delta, which is often called del. And so del of ZT is just ZT minus ZT minus 1. And let's see, where's, that's right. Yeah, and then I think that the typical notation is del squared of ZT, which is going to be del ZT minus del ZT minus 1, which is and what does that work out to? So that is ZT minus 2 ZT minus 1 plus ZT minus 2. And so and you might think, well, sometimes so is that difference time series meaningful, right? It's not, it's not the scale I'm interested in. But it turns out that we can do this. The purpose of doing the differencing is to get to time series that we can then apply these diagnostics, the ACF and the PACF, to get estimates of P and Q. The I, so ARIMA stands for autoregressive integrated moving average, and the I The integration is just the differencing. Okay, so the those models I was showing you that had P's, D's, and Q's. The D is the number of differences. Okay, so in practice you difference it until you get something that's stationary, right? So that's how you decide what the D should be. You look at that difference, that stationary time series, to figure out what the P's and Q's, how many lags for the autoregressive model, how many lags for the moving average model, and then you tell the computer to estimate all those parameters at once. Right? D is just it just says how many differences, but then the actual values of the P AR parameters and the Q MA parameters, and then the output of that is a model that is actually fitted and makes predictions on the scale of the original time series. So the actual equation. So just as we had here, right? We have this equation for autoregressive moving average. If we replace these W's with deltas from del W's from the difference time series and expanded those out, right? We could write out what that difference ARIMA model looked like on the original scale. It would be ugly, right? But it's still just a linear equation. So in many cases, or in some cases, the trend and the mean would be exponential rather than linear or quadratic. In that case, you need to log transform the data first, because that turns the exponential trend into a linear trend, and then you can difference it. And also, that's if you've got a non-stationary variance where the variance is approximately proportional to the mean, the log transform will also stabilize that. So in that case, then you'll be running the full analysis with however many number of differences on the transformed data set. Okay, so if you're doing some analysis of GDP, which tends to have an exponential trend, right? Your ARIMA model will actually be making predictions about log GDP. There is a class of models that deals more a more general approach dealing with non-stationary variances. This is a pretty well. This is an area I don't really know much about, so I'm not going to say anything about what goes into them. But just to let you know that such models exist. I think the G is for generalized and autoregressive. It's something like conditional heteroscedasticity. Do you work with those kind of models? That's right. Yeah. And then seasonality is a special case, which we'll talk about in a moment. So here's the workflow, right? If you're you have a time series and you want to apply an ARIMA model to it. First, you need to identify how many times it needs to be differenced, if it needs to be differenced. And then using the ACF and the PACF, find a tentative model, and by model I just mean the P and the Q, how many parameters for each of those processes, estimate the parameters, and then look at the residuals, right? And the residuals, as I said, it's do the residuals look IID and normal, and then and in particular, is there temporal structure? That we removed all the temporal structure from the residuals. So if we look at the ACF and the PACF of the residuals, our hope is that there are no significant correlations in either of those And if there is, then we need to sort of scratch our heads and go back and pick some different values for P and Q. So seasonal processes are a special case. So here's that time series of airline passenger miles. It's already been log transformed, so what was a exponential trend with increasing variance has become a linear trend with you know, the fluctuations are now pretty much, magnitude of fluctuations is not changing through time. So if we take, so there's two kind of trends to look at. There is this linear trend in the mean, which we can control by taking a first difference, right? And that's what this is. This is the same first difference. We're just taking these are monthly data, so it's just z of t minus z of t minus 1, right? And that controls the long-term trend, but although it's kind of hard to see the way these data are stacked up, you still have the annual cycle in these data. It's just that it's now you know, everywhere that this is coming down, you have negative